What if I told you that you could basically capture lightning in a box? Well, today we're diving into the world of capacitors, these incredible little devices that can store and release unbelievable amounts of energy in, quite literally, the blink of an eye. And when I say unbelievable, I mean it. Just look at this thing. This is the Z machine. And get this, for a few billionths of a second, it unleashes 80 times the power of every single power plant on Earth combined. No, that's not a typo. It's a critical tool in the race for nuclear fusion, and the whole thing is powered by a giant bank of capacitors. So that's the big question, right? How is that even possible? How can we pack that much energy into something and then unleash it all onto a target that's no bigger than a spool of thread? It sounds like science fiction. To get our heads around this, we've got to start with the basics. And, the absolute best way to think about a capacitor is to imagine it as a kind of electric spring. Okay, so by the book, a capacitor stores potential energy in an electric field. It's a bit like a battery, yeah, but here's the crucial difference. A capacitor can dump all of its stored energy almost instantly. And the key number for us is its capacitance. That's just the measure of how much juice it can hold. But let's go back to that spring idea, because it's just a perfect analogy. The work you put in to charge up a capacitor is exactly like the work you do to stretch a physical spring. You're just building up all this potential energy that's sitting there, ready and waiting to be let go. And this is where the analogy gets really, really cool. With a spring, its energy depends on how far you stretch it, right? Well, a capacitor's energy depends on how much charge you've managed to pack in. But here's the clever part. The stiffness of the spring is like the inverse of capacitance. So think about it. A low capacitance is like a super stiff spring. It's really hard to charge. But a high capacitance, that's like a nice stretchy spring, way easier to load up with energy. So we've got our electric spring. That's a great start. But to get to the kind of power we saw in the Z machine, we need to supercharge it. And that's where our capacitor's secret weapon comes into play, something called a dielectric. So the question becomes, how do we make that spring stretchier? How can we get it to hold way, way more charge, and therefore a lot more energy, without having to work a lot harder to do it? Well, the answer is almost ridiculously simple, but it has profound effects. You just take a special insulating material, called a dielectric, and you slide it right in between the capacitor's metal plates. That's it. That's the secret sauce. Now, this simple little addition does three absolutely critical things. First, it physically keeps the plates from touching each other, which is kind of important. Second, it's a way better insulator than plain old air, so you can crank up the voltage without sparks flying everywhere. And third, and this is the big one, it dramatically increases the capacitance. It makes our electric spring much, much stretchier. And we actually have a way to measure this boost. It's a number called the dielectric constant, which we just label with a K. Think of it as a simple multiplier. So if a material has a K of, say, 10, that means it boosts the capacitor's energy storage capacity by 10 times, compared to just having a vacuum or air between the plates. So you've got to be asking, how does an insulator do this? How does putting a non-conducting material in the middle actually make the capacitor better? Well, it all comes down to something really cool happening at the atomic level, a sort of molecular dance. And this dance, it has a proper scientific name. It's called polarization. It's basically the way charges inside the dielectric material itself rearrange when you put them in an electric field. So imagine the molecules inside that dielectric are like tiny little compass needles. Normally, like you see on the left, they're all just pointing in random directions. Total chaos. But then you apply an electric field by charging up the capacitor plates, and bam! They all snap to attention and line up with the field, just like you see on the right. And here is where the magic happens. When all those little molecules line up, they create their own tiny electric field that actually pushes back against the main field from the plates. Now, this opposing field weakens the overall field inside the capacitor. And it sounds weird, but by making the total field weaker, it actually makes it easier to pile even more charge onto the plates. It's like it makes more room for energy, massively increasing the capacitor's total storage. And this chart really shows you just how big of a difference this molecular dance can make. So a vacuum is our baseline, a 1. Air is barely any better. But look at glass. It boosts capacitance 5 to 10 times. Water, which is actually a fantastic dielectric, boosts it by over 80 times. And then you get to these crazy engineered materials like strontium titanate, which can increase the energy storage by a factor of 310. It's incredible. So let's pull this back from the molecular level to the world that you and I actually live in. Because this one simple principle, it's at the heart of technologies that are both absolutely gigantic and totally microscopic. We started with the Z machine, right? Well, its insane, mind-boggling power is only possible because its capacitors are filled with a dielectric. In its case, it's actually water that lets them store a truly immense amount of energy before they dump it all at once for those fusion experiments. But the very same principle is at work in something you've definitely seen before, a camera flash. A capacitor charges up, stores that energy nice and steady, and then when you hit the button, boom! It discharges everything in an instant through that flash tube to create that brilliant burst of light. Now, here is a really clever application, a stud finder. It works by creating a capacitor, where one plate is inside the device and the other plate is, well, it's the wall itself. As you slide it along, the material between the plates, or dielectric, changes from just drywall to drywall plus a wooden stud. That changes the capacitance, and the little device is smart enough to detect that change and tell you exactly where the stud is. And then we go to the total opposite extreme. Your smartphone has hundreds of tiny capacitors inside it. They are absolutely essential for everything, from the brain of the phone to the microphone to the screen you're touching. And every single one uses a special ceramic dielectric to cram as much capacitance as possible into a microscopic space. And that really is the most amazing takeaway. It's the exact same fundamental principle at work. That little molecular dance of polarization is what powers both room-sized nuclear experiments and the countless tiny components that make our modern world even possible. So it really leaves us with a fascinating question to chew on, doesn't it? We figured out this incredible trick of storing huge amounts of energy and releasing it in an instant. As we invent even better dielectric materials, what will the next generation of energy storage make possible? What's coming next?